What if even something that sounds straightforward, like the expansion rate of the universe, turns out not to agree? At first glance, it feels like a minor technical detail, the kind of thing you'd argue over whether a pizza fresh out of the oven is 32 centimeters or 34 centimeters across. But in cosmology, that number is the cornerstone on which we build our entire understanding of the universe. And here's the strange part. After decades of measuring, calculating, tweaking, debating, and even shouting at conferences, scientists still can't agree on how fast the universe is expanding. They've given this disagreement a dramatic name, the Hubble tension. To see why the expansion rate matters so much, let's rewind to Edwin Hubble. In 1929, he announced that the universe wasn't static, as Einstein once hoped, but expanding. Galaxies were fleeing from one another, and the farther away they were, the faster they moved. That discovery became the foundation of modern cosmology and gave rise to the Big Bang model, a universe born from a hot, dense point that's been growing for 13.8 billion years. To measure that growth, scientists defined the Hubble constant. Think of it as the universe's heartbeat. For every megaparsec of distance, about 3.26 million light-years, galaxies move apart by a certain number of kilometers per second. If we can pin down this cosmic pulse, we can figure out the universe's age, its size, and even its fate, whether it will keep expanding forever, slow down, or collapse. But here's the problem, and it's only getting worse with time. There are two main ways to measure the Hubble constant. One is by looking close to home, observing Cepheid stars and supernovae, then using them as cosmic yardsticks to measure expansion. This method gives about 73 kilometers per second per megaparsec. The other is by looking far back in time at the faint glow left over from the Big Bang, the cosmic microwave background, CMB. That's essentially a baby picture of the universe when it was only 380,000 years old. By studying tiny ripples in that light and plugging them into the standard model of cosmology, scientists get about 67 kilometers per second per megaparsec. Seems like a small difference, right? 67 versus 73. Like someone saying you're 5'7" instead of 5'10". But in cosmology, that's enormous. It's not just experimental error. Both methods have been refined to near perfection, and independent teams using different tools consistently get the same results within each method, which suggests nobody's measuring wrong. Instead, the problem may be deeper. Maybe the model of the universe we've been using all along is flawed. Enter the James Webb Space Telescope. With its giant 6.5-meter mirror, Webb isn't just the most powerful eye ever launched into space. It's a time machine, peering farther into the past than any telescope before it. It began probing ancient galaxies, early stars, and faint relics of the Big Bang. But instead of resolving the tension, Webb only made it worse. Webb confirmed that when you use nearby yardsticks, the expansion rate still comes out higher. When you go back to the cosmic microwave background, it's still lower. Neither side seems wrong. And worse, Webb hinted that the gap may not just be a technical hiccup. It could be a real crack in our understanding of physics. Maybe dark energy is stranger than we thought. Maybe dark matter behaves in ways we've never imagined. Some even whisper that Einstein's general relativity, the bedrock of modern physics, might need rewriting. It's like reading a murder mystery where every clue fits, the culprit is revealed, everyone relaxes, and then, in the final chapter, a supposedly dead character strolls into the living room and says, "Hi there." That's what the Hubble tension feels like to cosmologists. And this disagreement isn't just about numbers on a lab report. It could reshape our picture of the past and future of the universe. If the expansion rate is higher, the universe might be younger, closer to 12.5 billion years instead of 13.8. If it's lower, it could be older, and our timeline of how galaxies, stars, planets, and even life itself formed would need rewriting. Some compare the situation to assembling a 1,000-piece puzzle. You've put together most of it, the picture looks complete, but one piece just won't fit. You try flipping it, trimming it, forcing it, but it doesn't belong. That's the Hubble tension. And if one piece doesn't fit, maybe the entire puzzle was printed wrong from the start. The scientific community is split. Some argue this is just a subtle measurement error. With patience, we'll sort it out. Others insist, no, this is the sign of a coming physics revolution, just like when Einstein upended Newton. So does James Webb solve the Hubble tension? Not really. It's like inviting a mediator to calm an argument, only for them to show up with new evidence that makes both sides even more convinced they're right. Now nobody's backing down. If this were a boxing match, Webb just rang the bell to end round 1, and the fighters are gearing up for round 2. But no matter the final answer, one thing's certain: we're living through a historic moment in cosmology. Headaches like the Hubble tension are often the first hints of breakthrough discoveries. After all, nobody wants the universe to be too predictable. If everything fit neatly, we'd never stumble upon deeper truths. Sometimes, it's the numbers that frustrate us most that open the door to something profound. So, is the universe really expanding at 2 different speeds? Or are we just missing a piece of physics no one's dreamed of yet? The answer is still out there. But one thing is clear: this cosmology crisis is only the beginning, because the surprises waiting ahead are likely far greater. If the universe was just a few 100 million years old, a cosmic toddler, why were there already these massive ancient giants lounging around the playground? It sounds backwards, but that's exactly the puzzle James Webb handed to cosmologists when it spotted at least 6 enormous galaxies that existed only a few 100 million years after the Big Bang. They're too big, too old, and by everything we thought we knew about cosmic evolution, they simply shouldn't be there. Picture this: you're at the starting line of a marathon. The race has barely begun. You've just grabbed your water bottle, and suddenly someone next to you is already wearing a gold medal, saying, "I'm done." You'd be baffled. Wait, the race just started. That's pretty much how scientists felt when they saw these galaxies. According to our standard picture, after the Big Bang, the universe was filled with hydrogen and helium. Gas clouds condensed, forming the very first stars, so-called population 3 stars. They burned hot and fast, then exploded, seeding heavier elements and paving the way for the next generations of stars. Over hundreds of millions to billions of years, these cycles gradually built up giant galaxies like the Milky Way, with hundreds of billions of stars. In short, galaxies are like slow-cooked stews. You need time. You don't just whip one up in 5 minutes. But Webb uncovered these cosmic stews, already fully simmering just a few 100 million years after the universe's birth. 6 galaxies with masses equal to, or even greater than, the Milky Way, meaning they had already gathered hundreds of billions of stars when the universe was barely out of infancy. In other words, these giants ripened impossibly fast, and our current models can't explain how. Scientists gave them a dramatic nickname: universe breakers. Not because they're literally breaking the cosmos, but because their very existence shatters the framework we thought was solid. It's like working on a 1,000-piece jigsaw puzzle that's coming together nicely, only to discover 6 pieces that are the wrong color, the wrong shape, and don't fit anywhere. You can't throw them out. They're clearly real, but you also have no clue where they belong. To salvage the picture, a few ideas have been floated. Maybe Webb's mass estimates are off. Maybe the galaxies look huge but are actually puffed up with gas and dust, making them shine brighter than they really are. Maybe we're not gauging the age of the universe at that epoch correctly. But the unsettling possibility is this: if all the measurements are right, then galaxy formation happened far faster than we ever predicted. The universe might have found a shortcut, a way to hack time itself to fast-track the growth of fully fledged galaxies. It's like planting a seed today and waking up tomorrow to find a towering oak tree shading your yard. Impossible in our everyday world, but the cosmos doesn't seem to follow our rulebooks. Some researchers even suggest these universe breakers are a sign that modern physics is incomplete. Maybe dark matter, which makes up more than 80% of the universe's mass, helped galaxies clump together faster. Maybe dark energy, usually blamed for pushing the universe apart, has more complex behavior that sped up the process. A few daring voices even wonder if Einstein's general relativity doesn't quite hold in the newborn universe. And here's the kicker: these early giants aren't just a curiosity. They trigger a cascade of questions. How did their stars produce heavy elements so quickly? How did cosmic dust form in time? Could planets have appeared much earlier than we imagined? If these galaxies truly existed, then maybe life itself could have arisen far sooner than we ever thought. Of course, not everyone's convinced. Some scientists remind us these are still early observations. Data can get refined, and flashy discoveries sometimes lose their luster as measurements improve. But regardless of the final verdict, James Webb has already planted a seed of doubt in our minds, and sometimes that seed is more important than the answer itself. There's also something symbolic about all this. Just as Webb began its mission, one of its very first discoveries was bold enough to shake the foundations of cosmology. Like a rookie singer stepping onto the stage and hitting such a high note that the entire orchestra stops and stares. Which leaves us wondering, if Webb revealed universe breakers in its opening act, what other shocks might it have in store in the years ahead? The most unsettling thought might not be the 6 galaxies themselves, but the possibility that they're only the tip of the iceberg. If there are 6, there could be 60, 600, or 6,000 lurking out there in the early cosmos. In that case, our theories won't just need patching up. They'll need a total rewrite. And the surprises don't even stop there. Because while some galaxies grew up impossibly fast, others seem to have gone the opposite way. They abruptly stopped making stars, as if they retired early while still young. But that's another story, another mystery Webb has brought to our cosmic doorstep. There's a question that feels almost like a fairy tale. How can a young galaxy, alive with energy and enormous beyond imagination, suddenly drift into an endless sleep? Astronomers call it the Sleeping Beauty galaxy. Unlike the fairy tale princess surrounded by a castle overgrown with vines, this galaxy is enveloped in a massive cloud of gas and dust, housing hundreds of billions of stars. And instead of dark magic, its mystery is written in the language of cosmic physics. The story begins as the James Webb Space Telescope gazes into the early universe, a time when galaxies should have been at their most vibrant, exploding with star formation. This was the universe's childhood, an era when clouds of hydrogen glowed as they collapsed into colossal nuclear furnaces, unleashing the first light that pierced the primordial darkness. Yet, among countless bustling young galaxies, astronomers spotted a strange exception, a gigantic galaxy that seemed to have stopped. It remained there, massive and majestic, but no longer forming new stars. Picture a city growing at breakneck speed, skyscrapers rising, streets alive with movement, lights shining everywhere. Suddenly, construction halts, the lights go out, the streets empty, leaving a vast metropolis in eerie silence. That's the Sleeping Beauty galaxy. It's not just unusual, it challenges our fundamental theories of galaxy evolution. Why would a young galaxy act like a weary old sage? Current models suggest young galaxies are saturated with cold gas, the fuel for star formation. During the first 1 billion or 2 years, they should blaze with activity, producing stars at a dazzling pace. Yet observations reveal galaxies that only a few 100 million years after the Big Bang have already gone quiet. No new stars appear. It's as if a freshly fired engine has died, leaving a colossal vehicle stranded mid-journey. What could put such a massive, high-potential galaxy into hibernation? Several ideas exist. One is that a supermassive black hole at its center became too voracious, consuming matter at incredible speed and unleashing immense energy, either blowing away or heating the cold gas needed for star formation. Without fuel, the galaxy is forced to stop producing new stars, like an empty kiln with no clay to fire. Another possibility is that violent interactions between early galaxies, collisions and mergers, stirred and dispersed the gas. Instead of compressing into stars, the gas expanded and heated, sending the galaxy into dormancy. But these remain hypotheses. Current data isn't enough to determine the exact cause. What puzzles scientists most is the timing. Massive galaxies retiring is not unheard of. Today, we see enormous red galaxies that have almost stopped forming stars, but they reached that state after billions of years of evolution. Sleeping Beauty is different. It aged too quickly, almost as if an 18-year-old decided to retire and live a quiet, leisurely life. If these observations hold, our models of galaxy evolution need a rewrite. They suggest the life stories of galaxies are far more diverse than we imagined. Some burn with star formation for billions of years, others go quiet almost immediately, and some may even cycle through awake-sleep-awake phases multiple times. This also affects the potential for life. If a galaxy stops forming stars too early, it may never produce enough generations of stars to forge the heavy elements necessary for rocky planets, water, and ultimately, life. In other words, Sleeping Beauty galaxies could be cosmic dead zones, where life never has a chance to ignite. Yet from another perspective, their existence makes the universe more intriguing. If all galaxies followed the same path, the cosmos would be predictable, like a choir singing a single note. The emergence of unusual galaxies like Sleeping Beauty adds unexpected variation, enriching the cosmic symphony and sparking human curiosity. James Webb has opened a window into a universe that is not only vast, but astonishingly complex. A young galaxy may appear like a sleeping princess, producing no new stars, seemingly paused in time. But as in fairy tales, that sleep may not be permanent. Beneath layers of gas and dust, hidden mechanisms may yet awaken it. Perhaps a kiss from new physics, a theory not yet born, could rouse this cosmic princess. One thing is certain, with every Sleeping Beauty galaxy discovered, scientists are reminded how little we truly understand about galaxy evolution. And that makes the journey of discovery all the more thrilling, because the beauty of science lies not just in answers, but in the endless questions themselves. If a galaxy can age so quickly, what else in the cosmos might defy reason? The answers point to even deeper mysteries. Primordial black holes, massive beyond comprehension, challenging every law we thought we knew. A giant black hole appearing just 600 million years after the Big Bang. How is that even possible? The question cuts through the early symphony of the cosmos like a sharp, discordant note. According to everything we thought we knew, monsters like these shouldn't exist so soon. They're like towering ancient trees rising out of a desert after the very first rainfall. Too fast, too massive, and too far beyond what science expected. In the standard picture of the universe, supermassive black holes are supposed to be late bloomers. First, massive stars form. Some of them explode in violent supernovae, leaving behind stellar cores that collapse into small black holes, maybe a few dozen or a few hundred times the mass of the sun. From there, they grow slowly, swallowing matter around them, merging through cosmic collisions. It's a process that takes billions of years, like building a skyscraper one brick at a time. But then came James Webb, and it found things that looked nothing like a skyscraper being patiently assembled. Just a few 100 million years after the Big Bang, when the universe was still in its cosmic infancy, enormous black holes were already there. Not hundreds, not thousands of solar masses, but hundreds of millions, even billions. These weren't humble wooden huts. They were colossal towers rising almost instantly after the cosmic curtain lifted. That doesn't line up with the traditional story of stellar evolution. If black holes were supposed to grow from tiny seeds, then simply put, there wasn't enough time for them to get that big. The early universe was like a toddler just learning to walk, yet somehow carrying a mountain on its back. Physicists call this the ancient black hole paradox, a puzzle that shakes the very foundation of how we think galaxies and the cosmos evolved. So what's the answer? One leading idea is that maybe these giants didn't follow the usual star first then black hole pathway at all. Instead, they might have formed directly from massive clouds of primordial gas. This is the direct collapse scenario. Instead of breaking into stars, enormous hydrogen clouds collapsed straight down, creating black holes that were huge from the moment they were born. If that's true, then supermassive black holes aren't latecomers at all, but natural seeds of the young universe, giants that appeared at dawn. And then there's an even bolder idea: primordial black holes. These wouldn't need stars to exist. They could have formed in the very first moments after the Big Bang, springing directly out of tiny ripples in the density of matter itself. As these patches collapsed under their own gravity, black holes were born instantly. If real, they'd be relics from the very birth of time, silent witnesses to the universe's first heartbeat. And some physicists even suggest they might be the long-sought candidates for one of the biggest mysteries of all: dark matter. Even more astonishing, these early black holes weren't quiet. They were wildly active. Astronomers have spotted quasars, supermassive black holes devouring matter at furious rates, shining in the distant young universe. Their light outshines entire galaxies, which can only happen if the black holes at their centers were already enormous, too soon. Once again, the question echoes: how did they grow so fast? Some scientists push the idea further. Maybe we've been thinking about it all backward. Perhaps black holes and galaxies didn't evolve separately, but hand in hand from the very beginning. Maybe galaxies weren't the hosts that nurtured black holes. Maybe galaxies themselves were born around black holes, spun into existence by these gravitational giants. If so, the familiar story of the universe's origins may need to be rewritten from the ground up. The existence of these ancient black holes doesn't just challenge physics, it opens the door to the future of astronomy. Because if we can uncover the mechanism that allowed them to form, we'll learn something profound about how the universe itself began to operate in its first moments. This isn't just a side note, it's a central piece of the cosmic puzzle. Pause for a moment and take in the paradox. The universe, only 600 million years old, already hosting supermassive black holes. Compared to the current age of the cosmos, 13.8 billion years, that's like the first few hours of a human lifetime, a newborn baby with the heart of a grown athlete. If science is the universe's diary, then these black holes are an unexpected chapter, one no one saw coming. And like every great paradox in science, it's also a door to new ideas, new hypotheses, and maybe even revolutions in how we understand reality. We might be standing at a crossroads as profound as the one before relativity or quantum mechanics, when impossible observations turned out to be the very clues needed for the next great leap. A massive black hole only 600 million years after the Big Bang. It sounds like a contradiction, but it's real, and it dares us to expand our vision, to accept that today's impossibilities could become tomorrow's foundations of science. And the mysteries don't end there. Because James Webb has found something even stranger. Black holes that don't need galaxies at all. No home, no anchor. Just drifting through the cosmos like lone riders, carrying with them stories even harder to believe. A black hole not anchored to any galaxy, what does it even feed on? The question evokes a profound sense of loneliness, like a giant creature cast adrift in the cosmic ocean, without a home, without a community, simply drifting alone through endless darkness. We've given it a peculiar name, Cuson, a wandering black hole, lost in the vast void of space. When we picture black holes, most of us imagine bustling cosmic centers. They are gravitational monsters reigning at the heart of galaxies, devouring matter, gas, and even unlucky stars that stray too close. This image has become a familiar stereotype. Massive black holes paired with their galaxies, like hearts and bodies inseparable. But Cuson defies that pattern. It doesn't rely on a galaxy. No stars orbit it. No glowing accretion disk feeds it. It exists entirely alone, a lone warrior exiled from the battlefield. The first question that arises, how do we even know it exists? Black holes are inherently invisible. We detect them indirectly, through their effects on the surrounding space. For Cuson, the clue comes from a strange distortion, gravitational lensing. As this black hole drifts across a background star, its gravity bends the star's light, briefly making it appear brighter. Like a wandering magnifying glass, it inadvertently reveals itself. Through these subtle yet unmistakable signals, astronomers identified a solitary galaxy-less black hole for the first time. But if it has no galaxy, no abundant source of matter, what keeps Cuson alive? Here lies the universe's paradox. A black hole grows by consuming matter in isolation. Cuson lacks the rich fuel streams enjoyed by its cousins at galactic centers. It may survive on cosmic scraps, a wandering gas cloud, a small star nudged into its orbit, or even a faint trickle of interstellar material. A meager, scattered meal. Insufficient to shine brilliantly, yet enough to maintain its silent presence. This makes Cuson one of the most enigmatic objects in the cosmos. It doesn't glow, it's hard to detect, yet it hints at a universe teeming with wandering black holes we've never seen. Perhaps they are remnants of shattered galaxies, cast into exile by violent collisions. Or perhaps they formed in the universe's earliest chaos, never having a home galaxy to begin with. Imagine millions, or even billions, of such black holes drifting through space, invisible to our eyes. They emit no light, leave no loud signals, yet any unlucky star that passes nearby risks being swallowed in silence. In that moment, the universe is not just vast, it is far more dangerous than we ever imagined. A boundless ocean filled with hidden predators. QSON's existence raises a deeper question. Could wandering black holes play a hidden role in shaping the universe? If they are common, they may subtly influence the cosmic web, creating unexpected gravitational tugs that affect galaxy formation. They are no longer mere outliers. They become invisible hands, quietly reshaping the map of the cosmos. Some scientists even speculate that QSON might offer a window into primordial black holes. If these objects formed shortly after the Big Bang, it makes sense that they are not tied to galaxies. They could predate the larger cosmic structures, acting as the universe's first building blocks, or as lonely fragments left behind. Black holes are already mysterious, but a solitary wandering black hole magnifies that mystery exponentially. Picture QSON as a lone knight roaming the desert of space. No king, no kingdom, no allies. It is precisely this isolation that makes it a priceless subject of study, free from the chaos of galactic centers. Here, we can glimpse the raw, unadulterated nature of a black hole. Discovering QSON is like finding a lost journal page dropped along the universe's long journey. It reminds us that black holes are not only the hearts of galaxies, they can also be drifters, surviving outside every conventional rule. And who knows? These QSONs might hold the key to the next revolution in our understanding of the cosmos. A black hole without a galaxy, what does it feed on? That question remains unanswered. Yet QSON's existence is proof enough that the universe is full of surprises beyond imagination. And if you think a wandering black hole is the strangest thing out there, brace yourself. Being alone doesn't mean being weak. Some of these drifters feast at speeds that challenge even the fundamental limits of physics. A black hole devouring matter 40 times faster than physics says it should. What on earth is going on? This question has left not only astronomers, but even veterans of cosmic paradoxes utterly stunned. After all, we've long believed that black holes, no matter how ravenous, are kept in check by a strict rule, the Eddington limit. It's the delicate balance between gravity pulling matter in and radiation pressure pushing it back out. Like trying to pour water into a cup that's already full, the excess just spills over. And yet, out in the cosmos, there seem to be cups that not only hold the overflow, but somehow gulp it down at terrifying speed. One of the most shocking examples is the object known as LED 568. This black hole stands out not just for its enormous size, but for its bizarre, almost impossible appetite. Observations show it swallowing matter at about 40 times the Eddington limit. In other words, it's breaking the rules. To put it in perspective, imagine a person who can normally eat 3 meals a day. Suddenly you find someone who eats 120 meals a day and doesn't explode, doesn't collapse, but just keeps going. That sounds absurd. Yet for LID 568, that's reality. This discovery immediately raises a burning question. Is the Eddington limit really a limit, or is it more of a guideline, something that holds most of the time, but not always? If the latter is true, then our whole understanding of black hole and galaxy evolution might need a rewrite. One idea is that these impossible feeding frenzies don't last forever. Instead of constantly gorging, the black hole might go through short bursts, cosmic binges. In those moments, so much matter pours in that the light can't push it back fast enough, letting the hole consume more than usual. It's like a starving person suddenly seated before a feast. They devour it furiously for a few minutes before finally having to stop and breathe. If that's the case, then LID 568 isn't an outlier, but just one of many black holes that, at different times in cosmic history, have indulged in supersonic banquets. This could also explain why some supermassive black holes appeared so early in the universe. They grew at breakneck speed because, in their youth, they had these wild, short-lived feeding episodes that let them bulk up far beyond expectations. Another way to think about it is by looking at how matter falls in. Normally, it forms a bright, swirling disk around the black hole before getting swallowed. The radiation from that disk acts like a safety valve, limiting how fast the hole can eat. But if the infalling matter skips the disk and plunges inward chaotically in clumps and streams, then radiation pressure can't hold it back. The black hole can gulp faster, barely choking on the light at all. In other words, instead of sipping, it's slurping down the whole pot at once. And when astronomers zoomed in on LID 568, they noticed its light looked different from that of ordinary black holes. It flickered and shifted unpredictably, like a cosmic storm. Clouds of gas and shattered starlight seemed to tumble in, piece by piece, swallowed in a furious rhythm. If confirmed, this would open up a whole new way of thinking about black holes. They wouldn't just be slow, steady eaters, but chaotic, explosive, rule-breaking monsters. Quiet for ages, then suddenly erupting like volcanoes that lie dormant only to unleash catastrophic eruptions that reshape their surroundings. So the next big question is, what triggers these insane feeding frenzies? Why does LID 568 get to break the rules while most black holes still obey them? One tantalizing idea is that galactic collisions could be the culprit. When two galaxies crash together, or when massive gas streams are funneled into one spot, the black hole suddenly finds itself at an endless buffet. And when that happens, rules don't matter. It simply eats. If so, then these impossible feasts may not be rare at all. They could have been common in the chaotic, collision-rich early universe. That might be why young black holes swelled so unnaturally fast. They gorged themselves in cosmic banquets, well beyond any so-called limit. A black hole swallowing matter 40 times faster than physics should allow. What's really happening here? Maybe we're glimpsing the first clues that the universe doesn't play by the neat, simple rules we thought it did. The Eddington limit, once imagined as an unbreakable wall, now looks more like a flimsy fence, one that extreme conditions can smash right through. And as always, the universe doesn't stop at just one surprise. Because if impossible hunger can happen, then we're left with one more haunting question. Who or what sets the table for these feasts? The answer may lie in the most violent of cosmic collisions, moments when entire galaxies shudder and collide, creating exactly the conditions black holes have been waiting for. These monstrous appetites may, quite literally, be sparked by the chaos of the universe itself. Two galaxies race toward each other, colliding, twisting, and merging into a strange shape that looks almost like the number 8. Astronomers call it the Infinity Galaxy. Just the name itself feels poetic. Two cosmic giants meeting, binding together, forming a symbol of eternity. But behind this beautiful image hides a shocking scientific secret. That very collision may have sparked the birth of a monster black hole in a way we never imagined. In most cosmology models, supermassive black holes, the beasts at the hearts of galaxies, are thought to be the end result of countless stellar life cycles. Giant stars explode, leaving behind small black holes. Those smaller holes merge and feed, slowly growing into the giants we see today. It's a drawn-out process, taking hundreds of millions, even billions of years. But the Infinity Galaxy hints at another path, shorter, more direct, and far bolder. A black hole forming straight from the collapse of gas, skipping the deaths of stars entirely. Scientists call this scenario a direct collapse black hole. Picture an enormous cloud of gas. Instead of gathering to form new stars, it suddenly caves in on itself, collapsing straight into a black hole. No supernova fireworks, no gradual steps, just one decisive plunge. It's the difference between building a tower brick by brick and dropping a single solid block of concrete onto the foundation. The end result looks similar, but the speed and the mechanism are completely different. What makes the Infinity Galaxy so special is that its figure-8 structure seems to show this very collapse in action. When galaxies crash together, massive rivers of gas get squeezed into the center. Normally, that pressure and heat would ignite waves of new stars, lighting up the region. But here, instead of bursting into light, the gas seems to be sinking into darkness, collapsing, maybe, into a supermassive black hole right before our eyes. If that's true, it could solve one of astronomy's biggest puzzles. Why supermassive black holes appeared so early in the universe? For decades, scientists struggled with a timing paradox. How could black holes grow so enormous just a few 100 million years after the Big Bang? But if there's a cosmic shortcut through direct collapse, then the story makes far more sense. Instead of waiting billions of years, the universe could spawn these giants in just a few tens of millions. And it means something even bigger. The universe doesn't stick to just one script. It's more like a game with multiple paths to victory. Some black holes are built slowly, star by star, piece by piece. Others take the fast lane, skipping all the middle steps, forming almost instantly through direct collapse. The Infinity Galaxy may be the most vivid evidence yet of that second path. The figure-8 shape itself makes the story even richer. It's not just a pretty coincidence. It reveals how matter is twisted and crushed in the collision. At the two loops, stars and gas still swirl and glow. But at the center, everything is squeezed together, destabilized, and darkened. If that spot really is giving birth to a supermassive black hole, then we might be witnessing one of the rarest events in cosmic history, the creation of a black hole without the death of a single star. Some scientists are even asking, could the very first black holes, the primordial ones born right after the Big Bang, have formed the same way? Back then, the young universe was filled with pristine gas and almost no heavy elements, conditions that may have made direct collapse much easier. In that sense, the Infinity Galaxy isn't just a dazzling sight in the present. It could be a time machine, offering a glimpse of how the very first black holes came to be. For now, though, the evidence is still incomplete. The James Webb Space Telescope and others can only show us light and spectra, not the smoking gun of a newborn black hole. It could turn out to be just a dense, faint starburst, or some other exotic process we don't yet understand. And that uncertainty only makes the mystery more compelling. The universe rarely gives us neat answers. It prefers to leave room for wonder. No matter the final verdict, the Infinity Galaxy stands as a reminder of the universe's creativity. Galaxy collisions aren't just cosmic dances. They can be the birthplaces of monsters. It's beauty and brutality woven together, a graceful figure-8 hiding the ruthless reality of a supermassive black hole, two galaxies colliding into the shape of infinity, and maybe a black hole at its heart. It's a question that leaves us both awestruck and unsettled. Do all black holes arise from the brilliant deaths of stars? Or are some born in silence directly and unexpectedly? Because in the cosmos, collisions aren't always romantic. Sometimes, they're unimaginably violent. A galaxy torn into the shape of a jellyfish. Just how cruel can the universe be? When most of us think of galaxies, we imagine elegant spirals like vast cosmic flowers, or smooth ellipses glowing gently in the dark. But the universe doesn't always favor harmony and beauty. Sometimes it bears its raw brutality. One haunting example of this is the cosmic owl, a galaxy ripped apart into a bizarre shape, drifting through space like a giant jellyfish lost in the cosmic sea. Astronomers call this phenomenon a jellyfish galaxy. It happens when a galaxy plunges into an unforgiving environment, often a dense cluster of galaxies. These clusters aren't empty. Instead, they're filled with thin, scorching plasma. As a galaxy barrels through this plasma at incredible speed, the resistance creates a violent effect known as ram pressure stripping. Picture a car racing through a storm. Wind and rain hammer against it, peeling away loose paint. For a galaxy, the storm is far fiercer. The gas that fuels new stars is stripped away and swept behind it, forming long, glowing trails. The galaxy loses its balanced shape and drags along vast tentacles, like a jellyfish torn apart by unseen cosmic currents. The cosmic owl is one of the most spectacular cases. Its core is twisted, while glowing strands stretch hundreds of thousands of light years into space. These tendrils brim with clusters of newborn stars, sparked as the stripped gas collapses and ignites. In other words, the galaxy is being destroyed and giving birth at the same time, a strange scene that is both savage and creative. Its name, Cosmic Owl, isn't random. From afar, its shape suggests round, watchful eyes and long, outstretched wings, like an owl soaring across the stars, yet one torn apart by invisible forces. The name is also a reminder. For all its beauty, the universe is a ruthless place, where even colossal galaxies are helpless against the currents of cosmic violence. Jellyfish galaxies like the cosmic owl are more than just a spectacle. They're clues to how galaxies evolve. Stripped of their gas, they stop making stars. They become massive zombies, still holding their form, but fading inside. This process may be one of the main reasons many galaxies die young, aging long before we'd expect. Instead of a slow, natural decline, they're forced into early death by the harshness of their surroundings. And yet, this process is two-sided. On one hand, it kills galaxies, draining their ability to create stars. On the other, it produces glowing tentacles full of stellar nurseries, like trails of fire bursting into the darkness. Astronomers sometimes call it a kind of recycling. The death of one structure sparks the birth of new ones. The universe, it turns out, is both cruel and creative, destructive and generative at once. The intensity of ram pressure stripping depends on both speed and environment. The faster a galaxy plunges into a cluster, the more it suffers. In the cosmic owl's case, its insane velocity and the cluster's dense plasma tore away nearly all its gas, leaving us with an astonishingly clear jellyfish-like shape. On a deeper level, the cosmic owl forces us to reflect on fragility. Even a galaxy holding hundreds of billions of stars can be shredded by cosmic winds, reshaped into something strange and grotesque. If galaxies themselves are so vulnerable, then our solar system, tucked away in one spiral arm of the Milky Way, is little more than a speck of dust. But from that fragility comes perspective. The cosmic owl's tentacles are giving rise to new stars, and perhaps new planets, even new solar systems. One day, from the ashes of destruction, life itself could emerge again. In the cosmos, death and birth are never separate. They entwine like the two sides of a coin, like the torn but outstretched wings of an owl flying into the void. A galaxy torn into the shape of a jellyfish. How cruel is the universe? The answer might lie in images like the cosmic owl. Beautiful, violent, and paradoxical. They remind us that when we look up at the night sky, we're not just seeing silent twinkles of light. We're also witnessing cosmic tragedies unfolding far away. And yet, amid all this chaos, there's something even stranger. Hundreds of distant galaxies, scattered across the cosmos, all spinning in the same direction. Random chance, or a shared motion, dating back to the birth of the cosmos. That question first arose when astronomers spotted something astonishing. Hundreds of galaxies, scattered across mind-boggling distances, millions of light years apart, yet all spinning in the same direction. Like a troupe of cosmic dancers, separated by vast space, but somehow keeping time to the same invisible rhythm. Normally, we think of galaxy formation as messy and chaotic. After the Big Bang, matter spread out, clumped into gas clouds, then under gravity twisted and collapsed into galaxies. By theory, their spins should be random. One clockwise, another counterclockwise, with no preference. Like tossing thousands of coins, you'd expect a fair mix of heads and tails, never all one side. And yet, when scientists looked closer, they found something unsettling. Entire groups of galaxies, sometimes hundreds, choosing to rotate the same way. Picture a cosmic panorama, each galaxy a glittering spiral. Instead of pointing every which way, they all lean toward the same orientation, as if some unseen hand twisted them into alignment from the very start. This isn't just surprising, it shakes the foundations of standard cosmology. One bold idea suggests the universe itself may have had a kind of primordial spin. When the Big Bang erupted, perhaps space-time didn't just expand outward, but also carried a twist, like water swirling down a colossal drain. If true, then galaxies spinning in sync are fossils of that original cosmic rotation. It would mean that we and every galaxy live inside a universe that has been turning since its very birth. Of course, this is controversial. The standard model of cosmology rests on the assumption that the universe is homogeneous and isotropic. No direction is special. A built-in cosmic axis would overturn that, conflicting with decades of evidence from the cosmic microwave background to the large-scale distribution of galaxies. And yet, the alignment persists, defying simple explanation. Another possibility points to the universe's large-scale structure. Galaxies don't form in isolation. They gather along enormous filaments of the cosmic web. These strands, made mostly of dark matter, act like scaffolding, channeling how galaxies grow and spin. In this view, galaxy rotation isn't random, but guided by much larger flows of matter stretching across hundreds of millions of light years. Still, even this framework doesn't solve everything. The observed synchronization isn't confined to a single filament, but spreads across multiple regions. That raises the question, is there some hidden mechanism orchestrating hundreds of galaxies at once? Intriguingly, the phenomenon sparks a more philosophical idea. Maybe the universe has a kind of collective memory. If the cosmos is a self-organizing system, its first motions might leave lasting echoes, like the opening notes of a song that continue to resonate through billions of years. Galaxy spins wouldn't be accidents, but lingering rhythms from the universe's overture. This story isn't only about science. it reshapes how we see our place in the cosmos. Earth, the solar system, the Milky Way. Perhaps all of us are caught in a grander choreography, turning to a melody we cannot yet hear. Maybe we're nothing more than motes of dust swept into a cosmic whirl, yet still part of the same universal dance. And here lies a paradox. If galactic synchronization is real, why is it so hard to detect? Maybe our data only covers a small patch of sky, and the effect shows up only in special regions. Or maybe it's widespread, but its signal is buried under the chaos of billions of other galaxies. The James Webb Space Telescope and the next generation of observatories might help us find out whether this is a universal rule or just a rare coincidence. Whatever the answer, this alignment forces us to rethink. The universe may not be as random as we once believed. Beneath the apparent chaos, vast currents might be shaping the motions of hundreds of galaxies. If confirmed, we'd need to rewrite the opening chapter of the universe's origin story. Random chance or a shared cosmic motion? The question remains open. But the very fact that it exists reminds us the universe is far larger and stranger than we imagine. And in its endless spinning symphony, we may have only just heard the first few notes. Segue. And this strange cosmic alignment also makes us reconsider another puzzle, the fate of wandering planets. For even in the midst of cosmic chaos, hundreds of galaxies still spin the same way. More than 500 free-floating planets, some even drifting in pairs, wander through the darkness of the cosmos. These aren't worlds orbiting a star like Earth circles the sun, but cosmic castaways, thrown out of their home systems, or never bound to a star in the first place. They're like abandoned children, without an anchor, silently roaming the cold void. Recent telescopes, especially when peering into the Orion Nebula, the birthplace of countless young stars, have spotted these wanderers. Orion isn't just breathtaking with its glowing gas and dust, it also hides a strange theater where hundreds of rogue planets drift aimlessly. Even more haunting, some of them travel in pairs. Two planets with no star to cling to, bound only to each other, dancing endlessly in the dark. The image is chilling and beautiful. Two drifters finding one another and choosing to wander together. But why do they exist? One idea is that during the chaotic birth of star systems, some planets get flung out into interstellar space. Another theory suggests they form like stars, collapsing from clouds of gas, but never growing massive enough to ignite. Either way, the result is the same. Countless frozen worlds, lightless and sunless, adrift across the galaxy. And the story doesn't end there. Some of these wanderers send out strange bursts of radio waves. Imagine a planet lost in eternal night, whispering static into the void. Astronomers believe these signals come from powerful magnetic fields surrounding them. Even without a star to fuel them, some rogue planets still generate magnetic activity, sometimes strong enough for us to detect from Earth. That discovery shocked scientists, proving these worlds aren't lifeless husks, but may host complex, mysterious processes we barely understand. Picture landing on one. The sky would be absolute black, no sunrise, no sunset, just endless night. Temperatures so low that oceans would freeze solid, except perhaps deep underground, where the planet's core still leaks warmth. Down there, hidden beneath miles of ice, subsurface seas might exist, like those on Europa or Enceladus. If so, even these dark, exiled planets could cradle primitive life, surviving not by sunlight, but by geothermal heat. A terrifying, thrilling thought. What's even more mind-bending is their sheer number. Some studies suggest rogue planets could actually outnumber the stars in our galaxy. If that's true, the Milky Way isn't a sea of stars at all. It's a sea of planets, most of them invisible, drifting unseen in the dark. The universe may be far richer in hidden, silent worlds than in glowing suns. The big question, how do we even find them? Without starlight to reflect, they're nearly invisible. Astronomers rely on rare, indirect methods like gravitational microlensing, when a rogue planet passes in front of a distant star, warping its light for a fleeting moment. Discoveries like these gave us our first proof that such planets exist. But to uncover the billions more likely out there, we'll need far more powerful tools. Still, even with the little data we have, rogue planets are already rewriting our view of the cosmos. They're not exceptions. They might be the rule. Planets with stars, like Earth, could be the minority. The universe, then, isn't just a bright celebration of suns. It's a vast gathering where most of the guests stand quietly in the shadows. And that loneliness sparks the imagination. If life can exist in the hidden oceans of icy moons in our own solar system, why not on a rogue planet too? Perhaps somewhere in the cold dark, life has taken root without ever knowing the warmth of a star. So far, over 500 free-floating planets have been confirmed, and that's just the tip of the iceberg. The universe could be teeming with these drifters, worlds without dawn, without suns, surviving only in darkness. The more we think about them, the rarer and more fragile Earth seems. Our blue skies and steady sun feel like gifts against impossible odds. And yet, even these cold, wandering planets aren't the harshest environments out there. Because elsewhere, some worlds cling tightly to their stars, only to be turned into blazing furnaces, rivers of molten rock with temperatures beyond imagination. Welcome to 55 Cancri E. Imagine a world where the surface burns at over 2,000 degrees Celsius, hot enough to melt almost any metal. Mountains crumble into rivers of glowing lava, and instead of rain, the skies pour down heavy droplets of molten metal. This is 55 Cancri E, one of the strangest hellish planets ever discovered. But what truly shocks scientists isn't just its brutality. It's the fact that, against all odds, this inferno still manages to hold on to a thick atmosphere, as if defying the very laws of physics. Located about 40 light-years away, 55 Cancri E orbits the star 55 Cancri A, which is similar in mass to our Sun. The planet hugs its star at an incredibly close distance, just 1/25 the distance between Earth and the Sun. That means a year there lasts only 18 hours. Yes, in less than a single Earth day, this planet whips around its star once, bathed in unrelenting light and blistering heat. At such proximity, its surface is believed to be a vast ocean of lava. Every kind of rock, granite, basalt, you name it, melts into fiery streams that boil, evaporate, and rise into the atmosphere. Standing there, you wouldn't find solid ground beneath your feet, only a seething sea of magma, under a sky where there's no day or night, just eternal, blazing red light. And then comes the real paradox, the atmosphere. At temperatures above 2,000 degrees Celsius, you'd expect every molecule to simply vaporize into space. Yet observations from the James Webb and Spitzer telescopes reveal a dense atmosphere clinging to the planet. Its exact makeup is still unknown, but scientists suspect it's rich in CO2, CO, and vapors from molten rock. In other words, 55 Cancri E may have its own bizarre atmospheric cycle. Lava and volcanoes spewing gases upward, rock vapor condensing into clouds, and then raining back down as solid minerals or droplets of metal. It's like Earth's water cycle, but twisted. Instead of rain, there's metallic downpour. Instead of water vapor, clouds of minerals. Instead of rivers, glowing channels of lava. A storm on 55 Cancri E might mean molten iron or titanium splattering against the surface, sizzling like fireworks straight out of hell. The big question is, how does this planet even keep its atmosphere? One theory suggests its immense gravity locks the gases in place. Another proposes that constant volcanic eruptions continuously replenish the atmosphere, even as stellar winds try to strip it away. Either way, its existence forces scientists to rethink our entire understanding of how planetary atmospheres can survive. Inside, 55 Cancri E may hide even more secrets. Some studies suggest it could contain staggering amounts of carbon, possibly in the form of diamond. If true, beneath its molten surface might lie a glittering core of diamond and graphite. The idea of a diamond planet sounds poetic, but in reality, no one would live long enough to admire such beauty within its infernal seas. What's more, 55 Cancri E seems to experience strange climate shifts. Observations hint that its surface heat doesn't stay evenly distributed, sometimes concentrated on one side, sometimes spread across the whole globe. This could mean massive planet-wide eruptions, with boiling magma blasting into the air, forming dense clouds before collapsing back down as fiery storms. The atmosphere, in this sense, acts like a chaotic machine, constantly resetting itself, never stable. Compared to Earth, the contrast is staggering. Our water cycle brings gentle rains and drifting white clouds, sustaining life. On 55 Cancri E, the mineral cycle turns the planet into a burning engine with stone clouds and deadly metal rain. Two planets, both obeying the same physics, yet one becomes a lush paradise, the other a red inferno. This is the true richness of the universe, not just in the sheer number of planets, but in the wildly different ways they operate. From frozen loners drifting in darkness to scorched worlds like 55 Cancri E, the cosmos lays before us scenarios far beyond human imagination. Each discovery doesn't just amaze us, it forces us to rewrite the textbooks. And if you think 55 Cancri E is the peak of cosmic nightmares, just wait. There are worlds out there where magnesium clouds swirl, where iron rains from the skies, and where massive radio auroras light up the heavens. The universe, it seems, never runs out of surprises. Imagine a world where the sky isn't painted with soft white clouds, but with heavy layers of vapor made of iron and magnesium. As the temperature shifts, those clouds condense, birthing dense metallic raindrops that plummet toward the surface. It's nothing like the gentle rainfall of Earth. This is a storm of glowing iron bullets, each drop a molten shard tearing down from the heavens. The scene is both beautiful and terrifying, like nature staging a silent but brutal play. This strange world has a name, SIMP 0136, a rogue planet, a wanderer drifting free with no star to call home, no sun, no orbit, no anchor, just a loner adrift in the vastness. And yet, paradoxically, it isn't quiet. SIMP 0136 glows faintly in infrared, a dim ember visible to our telescopes. Look closer, and you discover something astonishing. Its atmosphere is loaded with iron and magnesium, building clouds unlike anything we've ever seen in the solar system. Rain here is unlike anything you know. A raindrop on Earth can float, shimmer, and dissolve into mist. But on SIMP 0136, an iron or magnesium droplet would blaze as it falls, searing through anything in its path. To stand beneath such a storm would mean being crushed, not just by weight, but by the unbearable heat of molten metal. In short, this is rain from hell, glorious, apocalyptic, and utterly unlivable. But SIMP 0136's wonders don't stop at iron rain. It also carries a far stranger secret: radio auroras. On Earth, auroras are shimmering curtains of light, born when the solar wind collides with our magnetic field. But SIMP 0136 has no star feeding it. So why does it blaze with auroras? Not in light, but in gigantic radio waves. Observations reveal its magnetic field is tens of times stronger than Earth's, so powerful it can trigger massive electrical currents in its own atmosphere, producing constant radio emissions. These signals are so strong that radio telescopes on Earth can pick them up, despite the planet being over 20 light-years away. In the eternal dark, SIMP 0136 is not silent at all. It roars in radio, like a wanderer refusing to vanish into the void. That leaves astronomers with a riddle. Is SIMP 0136 a planet or a failed star, a brown dwarf? With dozens of Jupiter's mass, it sits on the knife edge between giant planet and star that never was. This blur between categories only deepens the mystery. It's part planet, part star, an in-between creature of the cosmos. For perspective, compare it to 55 Cancri E. One is locked to its star, scorched into a glowing ocean of lava. The other drifts alone in darkness, yet pulses with radio auroras. Two extremes, one lesson. The universe never runs out of ways to astonish us. And SIMP 0136 invites a chilling thought experiment. If you could somehow stand on its surface, wrapped in indestructible armor, you'd see skies swollen with iron and magnesium clouds, glowing faintly against a backdrop of absolute black, for no starlight reaches here. Then, without warning, the entire planet would shudder as a colossal electrical discharge ripples through its magnetic field. A flash of radio aurora would erupt like invisible thunder, rattling you down to your bones. It's a scene almost beyond human imagination. The discovery of SIMP 0136 forces us to rethink what a planet even is. We once believed every planet must orbit a star, but the universe doesn't care for our definitions. A planet can drift alone, rain molten iron, breathe metallic clouds, and sing in radio waves. They exist outside our neat categories, wild and untamed. And perhaps the most humbling thought is this: planets like SIMP 0136 may not be rare at all. If the galaxy holds hundreds of billions of stars, then rogue planets could be even more numerous. Somewhere out there may be countless others, each one a bizarre experiment of nature, waiting to be uncovered. SIMP 0136 is not just an outlier. It's a reminder that the cosmos never stops inventing, never stops challenging our models, never stops stretching our imagination. And while it rains fire and shouts in radio waves, elsewhere in the universe are worlds so strange, they vanish before our very eyes. One of the strangest feelings in science is when you think you've just caught solid evidence in your hands, only to watch it dissolve like a mirage. In astronomy, that feeling is almost routine, because everything we see in the night sky comes from light that has traveled for years, sometimes millions of years, before reaching us. Which means that every so often, a discovery turns into nothing more than a cosmic prank. This story begins with the James Webb Space Telescope, humanity's newest pride and joy, turning its gaze toward Alpha Centauri, the closest star system to us, just 4.3 light-years away. For generations, Alpha Centauri has been a symbol of curiosity. If humanity ever leaves the solar system, this would likely be our very first stop. So when Webb picked up signs of a planet orbiting that star, the entire astronomy community held its breath. The planet appeared to be small, tucked close to its star, its atmosphere reflecting just enough light to reveal its presence. It wasn't another Earth, but the simple fact that a planet might exist right next door was enough to set our imaginations on fire. People began sketching futures where robotic probes or even more advanced telescopes would one day explore it in detail, searching for the faintest hints of life. But the excitement didn't last. With further observations, the planet vanished. No signal, no reflected light, no trace of a world orbiting Alpha Centauri. A headline-making discovery evaporated into an unsettling mystery. What happened? A few possibilities emerged. The first, the planet might still be there, but hidden in a part of its orbit that makes it almost impossible to spot. Most exoplanets are detected by watching their star dim as they pass in front, or by measuring tiny wobbles in the star's position. But if the orbit isn't aligned just right from our perspective, the planet could simply be playing hide-and-seek with us. The second, cosmic dust. Thick clouds of dust can scatter or block starlight in ways that mimic the signal of a planet. What Webb saw might not have been a planet at all, but a dense cloud of gas and dust briefly reflecting light before dispersing. Around young or active star systems, such dust storms are anything but rare. And the last possibility, the most disappointing one for our imagination, is that there was never a planet to begin with. Just a false signal. A coincidence in the data, amplified by our eagerness to find something extraordinary. In other words, a scientific mirage. Whatever the truth, the disappearance of the Alpha Centauri planet left behind a haunting lesson. It reminded us that finding new worlds is never straightforward. Sometimes the universe teases us with a wink, then pulls it away, as if testing our patience. But it also sparks even stronger curiosity. If such a planet does exist, it would be a turning point for both astronomy and science fiction alike. If not, then its very disappearance forces us to ask new questions. Have we truly understood how planets form and survive around nearby stars? Here's the interesting part. Even if the Alpha Centauri planet has slipped through our fingers, it doesn't dampen humanity's desire to search. On the contrary, it highlights the possibility that young or unusual star systems could host planets forming in ways we've never imagined. Maybe Alpha Centauri isn't hiding a world after all, but other young systems might harbor stranger stories. Planets born into bizarre orbits, with fragile atmospheres or wild, unpredictable changes. Think about it. If a planet can simply vanish from our view in just a few years, how many more illusions are still waiting out there in the dark? Each false lead, each fleeting signal, is still a step closer to the truth. So maybe we shouldn't call this a failure at all. Maybe it's a reminder that the universe never gives up its secrets easily, that it always hides behind layers of mystery, daring us to keep looking. And perhaps, hidden in those dusty, chaotic young star systems, we'll eventually find the missing pieces of how planets really come to be. Imagine watching a young planetary disk where rocks and gas begin to gather, ready to form entirely new worlds. In most cases, water plays the central role here, laying the foundation for oceans and life-friendly atmospheres. But in the infant star system Sui 10, astronomers stumbled upon a very different picture. A disk almost devoid of water, yet thick with carbon dioxide. This raises a profound question. If planets grow out of such a disk, could life ever take hold? On Earth, water is indispensable. It dissolves compounds, carries nutrients, and enables the chemistry of life itself. But what if a planet emerges with only CO2? Its atmosphere could be dense and suffocating, its surface hot and hostile. Could the seeds of life sprout in such a place? The more astronomers looked at Shui 10, the stranger it became. They found far more carbon dioxide than expected, and the dust wasn't evenly spread. Some regions were dense with tiny particles, while others were nearly empty. This hints that planet building here doesn't follow the usual blueprint. Instead of forming out of evenly distributed matter, planets may coalesce from clumps of dense material, leading to worlds born asymmetrical, with atmospheres and chemistry radically unlike Earth's. Even the pace of formation is unusual. In Shui 10, some planets may reach impressive sizes in just a few million years, much faster than traditional models predict. These worlds could absorb CO2 directly from the surrounding disk, rather than waiting on slow chemical reactions or collisions. That means they develop thick, suffocating atmospheres almost immediately, entering existence already extreme. And it isn't just chemistry that's odd. The orbits themselves are eccentric, literally. Instead of circling smoothly, these planets swing closer to and farther from their star in dramatic cycles. As a result, their surfaces may swing wildly from scorching heat to near-frozen cold. This instability makes it even harder to hold onto water. Any trace amounts could quickly boil away or freeze solid, leaving behind barren deserts or frozen wastelands. Scientists suspect that if life were ever to appear in such an environment, it would have to adapt with incredible speed, or exist in ways we can barely imagine. The chaos doesn't end there. These young planets appear to tug fiercely on one another, their gravity causing collisions, orbital shifts, even stripping gases from each other's atmospheres. In some cases, a larger world might steal material from a smaller neighbor, creating dramatic imbalances in composition and structure. It's a messy, violent process, but one that could give rise to strange, new kinds of planets. Shui 10 is not unique, but it's a striking reminder. The universe doesn't have to produce Earth-like worlds. Each young star system, its own laboratory, running experiments in planet making. A planet rich in CO2, a world without water, a planet on a wildly eccentric orbit, all are proof of cosmic diversity. Viewed another way, these planets might be prototypes of extreme worlds. Places where life, if it exists, doesn't rely on water at all, but instead on other chemical pathways, or adapts to atmospheres that are crushingly thick and constantly shifting. That possibility widens our imagination. Somewhere out there may be life completely unlike anything we've ever envisioned, thriving in places our eyes could never hope to recognize as habitable. From systems like Shui 10, we learn that planet formation isn't just matter gathering under gravity. It's a complex dance of collisions, volatile atmospheres, and unstable orbits, producing worlds that defy our expectations. Every planet, every atmosphere, every chemical cycle is a product of chance, yet intricately woven into the fabric of the cosmos. When astronomers look at Shui 10, they don't just see newborn planets. They glimpse the universe experimenting with the conditions for life, expanding the boundaries of human imagination. If a planet can form without water, yet still grow a heavy atmosphere, then we must accept a startling possibility. The cosmos holds stranger worlds than we've ever dreamed, where heavy elements and complex chemistry may appear far earlier than we thought. And as we look deeper into the ancient universe, we find stars that forged heavy elements far too soon, reminders that cosmic history is full of surprises. When we picture the early universe, most of us imagine a simple expanse made almost entirely of light elements, mainly hydrogen and helium. But recent observations have painted a very different picture. Oxygen, carbon, nitrogen, the heavy elements essential for life, were already present shockingly early, leaving astronomers both fascinated and puzzled. According to the classic theory of stellar cycles, these elements should only appear after many generations of stars, as older stars die, explode, and enrich the cosmos with new material. Yet the evidence tells us that heavy elements were already around in the young universe. These first stars seem to have been able to forge oxygen, carbon, and nitrogen at an astonishing pace, just a few 100 million years after the Big Bang. This creates a paradox. How could these primordial stars produce elements that, in theory, should have required countless stellar generations to accumulate? Scientists now call this one of the great origin mysteries of the cosmos. From infrared light to the spectral signatures of distant galaxies, every line of data suggests that heavy elements showed up far earlier than any models had predicted. One idea is that these stars were truly colossal, burning fast and bright. Their lives were brief but intense, racing through fusion reactions that quickly created heavy elements, then dying in early supernova explosions. Those explosions released vast amounts of oxygen, carbon, and nitrogen into their surroundings, enriching cosmic gas and dust clouds right in the universe's infancy. In turn, the next generations of stars and planets were born into environments already seeded with the building blocks of life. This upends the traditional view of stellar evolution. If heavy elements formed so early, then our models must change. Could there be unknown mechanisms of element production? Or perhaps unique types of stars existed only in the universe's first chapters, creating heavy elements in ways we've yet to understand. To chase answers, scientists are turning to new observations, from telescopes like James Webb to sophisticated simulations of stellar evolution. Another intriguing twist lies in how these heavy elements were distributed. Observations reveal they weren't everywhere, but clustered in young galaxies blazing with massive stars. That paints a very different picture. Not a chemically barren early cosmos, but a turbulent one dotted with chemical hotspots of oxygen and carbon glowing amid the vast seas of hydrogen and helium. The early presence of oxygen, carbon, and nitrogen suggests something profound. Life's raw ingredients didn't take billions of years to appear. Even as the young cosmos expanded, the seeds of biochemistry were already sown. This opens the possibility that primitive planets, just a few 100 million years post-Big Bang, may have had the materials to form complex organic compounds, even if conditions were still harsh. It also ties directly to ancient wandering objects, like the interstellar comet 3I Atlas. If heavy elements existed early, then comets and asteroids born in those times could carry them across the universe, serving as messengers of creation. Atlas is one such messenger, over 7 billion years old, older than our solar system itself. It bears ancient chemical fingerprints that prove heavy elements were already moving freely across space long before Earth was even formed. These discoveries don't just reshape our view of stars, they reshape our view of life's possibilities. If oxygen, carbon, and nitrogen were part of the cosmic landscape from the start, then even the youngest, strangest, or most isolated planets could have had the chemistry needed to spark prebiotic reactions. Worlds without suns, or planets in brutal environments, may still belong on the map of life in the universe. And the message from these early element-forging stars is clear. The universe doesn't wait for us to figure it out. It creates, it spreads, it rearranges matter in ways that defy our neat equations. Every new observation, every ancient comet, every young star rich in heavy elements is a reminder that the universe always stays one step ahead of human imagination. These young stars also challenge our models of galactic evolution. By enriching their surroundings so quickly, they reshape the conditions that later stars and planets had to adapt to, shaping atmospheres, planetary systems, and even the earliest chances for life. And once again, this story connects us back to a wandering relic from deep time, the interstellar comet 3I Atlas. Imagine an object drifting through the darkness of space, untethered to any star system, wandering the cosmos for more than 7 billion years. Older than our own solar system, it is a lonely traveler carrying secrets from the universe's earliest days. That object is 3I Atlas, the first interstellar comet ever discovered with such ancient origins. A messenger between the stars, it preserves a chemical story that began when the first heavy elements came into existence. 3I Atlas first revealed itself as it skimmed past our solar system, captured by James Webb and powerful ground-based telescopes. Its sudden arrival sent the scientific community into a frenzy, mobilizing every possible instrument to observe it. Unlike the comets we're familiar with, 3I Atlas doesn't orbit the sun or any star at all. It moves freely, its vast trajectory spanning thousands, perhaps millions of star systems without ever being pulled in by gravity. That freedom means it has preserved much of its original chemistry, untouched by the intense heat of a nearby star. Spectral analysis shows that 3I Atlas carries the raw ingredients of the early universe: carbon, nitrogen, oxygen, and complex organic compounds that have survived intact. It's like a cosmic archive on the move, holding clues to how elements were distributed and accumulated in the dawn of time. Through it, astronomers can read the universe's chemical history, tracing how heavy elements traveled between infant stars and planets. What makes 3I Atlas even more remarkable is that it doesn't just preserve chemistry, it demonstrates how material is transported across the cosmos. As it wandered through countless star systems, it enriched dust clouds and spread heavy elements slowly but steadily. It is living proof that heavy elements are not only created, but also dispersed across the universe, laying the groundwork for new stars and planets to form in chemically rich environments. Its resilience is another mystery. For billions of years, 3I Atlas has endured radiation, collisions with cosmic dust, and the gravitational pull of passing stars and galaxies, yet it remains nearly intact. This survival makes it an extraordinary natural time capsule, keeping the universe's chemical memory alive for us to study. Then there's its speed and path. Unbound by any star, 3I Atlas races through interstellar space at incredible velocity, slicing across regions few objects can traverse. For humanity, this is a rare chance to witness such a traveler. But it also raises profound questions. Where did it begin its journey? Was it ejected from a destroyed star system, or born from the violent collisions of the early universe? Current models can't fully explain its ancient voyage, making it one of the great puzzles of modern astronomy. At over 7 billion years old, 3I Atlas predates the solar system by nearly 3 billion years. Long before Earth existed, before the sun began to shine, this comet was gliding through untouched cosmic wilderness, carrying the chemical fingerprints of an era just a few hundred million years after the Big Bang. That's why scientists see it as a true ancient messenger, a bridge between the universe's infancy and our present, offering a glimpse of the physical and chemical conditions that once prevailed. Its importance also lies in how it connects to other discoveries. The early appearance of heavy elements, the strange young exoplanets rich in CO2, even the so-called rogue planets, all may be linked to the way ancient objects like this transported matter across the stars. 3I Atlas isn't just a comet. It's evidence of a vast cosmic network, weaving planets, stars, and chemistry together over billions of years. And perhaps the most tantalizing question of all, what if a young planet absorbed material from a comet like this? Could it spark the formation of organic compounds, the very seeds of life, at a time when the universe itself was still in its youth? If so, Earth may not be unique. Countless other worlds could have been chemically seeded by interstellar wanderers like 3I Atlas, hinting that the potential for life is far more widespread than we once imagined. Yet even as we marvel at this cosmic traveler, the universe reminds us it still holds stranger mysteries. Among them are the glowing little red dots in the distant early cosmos, enigmatic lights that hint at forces and matter we've never encountered before. In a distant corner of the young universe, the James Webb Space Telescope captured a strange phenomenon that left astronomers holding their breath. They saw more than 300 glowing red specks shimmering against the vast darkness, far brighter than anything else from that same cosmic era. Tiny yet unusually radiant, they challenged nearly every traditional theory about how galaxies or black holes form. These mysterious objects were given a deceptively simple name, the little red dots. The question is, what exactly are they? Each red dot might be a newborn galaxy, forming at a breathtaking pace, or perhaps a supermassive black hole, ravenously devouring matter. Some astronomers have even suggested something more radical, that they could represent an entirely new kind of matter, something never before observed, capable of reshaping our understanding of matter and energy in the cosmos. What makes the little red dots so remarkable isn't just their brilliance, but also their distinctive color. Their crimson glow isn't simply the result of cosmic redshift. It also reveals unusual chemical and physical traits unseen in other young galaxies. Their spectral signatures carry clues about temperature, density, and extreme energy processes at work within them. Yet none of these signals neatly match existing models. Even more astonishing is their age. The little red dots appear at a time when the universe was only a few 100 million years old. Current theories suggest galaxies should have been rare back then, and supermassive black holes even rarer. Yet here they are, bright, energetic, undeniable. Their existence proves the early universe was not weak or fragile, but rather chaotic, diverse, and bursting with energy. One of the greatest challenges lies in uncovering their true nature. If they are galaxies, they must have formed stars at record speed, compressing enormous amounts of matter into compact regions, unleashing vast amounts of energy in only a few million years. If they are black holes, their feeding rates would defy every known limit, like cosmic supereaters, but even more extreme than any we've seen before. And if they represent some new kind of matter, the discovery would shake physics to its core, opening an entirely new chapter in our understanding of the universe. Observations also reveal something even stranger. The little red dots don't appear randomly scattered. Instead, they seem to cluster in patterns, hinting at hidden forces or structures shaping their arrangement. It's possible the young universe already followed blueprints we have yet to imagine, and these dots may be the first signposts of those cosmic designs. Their brilliance gives astronomers an extraordinary opportunity to study how stars and galaxies formed under the most extreme conditions. If they're galaxies, they reveal how matter and energy interacted in searingly hot, ultra-dense environments. If they're black holes, they provide unprecedented data about the limits of matter consumption and energy release. In either case, each dot is like a living laboratory inside the early universe. There's also the possibility that the little red dots connect to other cosmic mysteries. They might be the seeds of giant galaxies, the ancestors of colossal black holes, or even related to dark matter structures that remain invisible to us. Perhaps they even help explain puzzles like the synchronized rotations of galaxies or the insatiable hunger of ancient black holes. Above all, these dots remind us that the early universe was anything but empty. It was alive with violent physics, strange chemistry, and phenomena that strain the boundaries of our theories. Every time we peer deeper into space, the universe surprises us with something new. And the mystery doesn't stop with what glows. It may also lie in the invisible frameworks, the cosmic magnetic webs linking galaxies like neurons in a brain, that hinting at levels of order and connection we've only just begun to glimpse. When we look up at the night sky, we usually think of stars, galaxies, or black holes. But there's another invisible layer of reality shaping the cosmos that often goes unnoticed: magnetic fields. They're not just swirling around planets and stars. Magnetic fields stretch across vast cosmic scales, weaving between galaxies, threading through gas and dust, forming a hidden structure that scientists are only beginning to uncover. A recent discovery has left astronomers stunned. Ancient magnetic fields in the early universe appear to have been organized into intricate networks, eerily similar to the web of neurons in a human brain, as if the universe itself had found a way to self-organize. Observations from radio telescopes and the James Webb Space Telescope reveal that these magnetic fields aren't just simple lines linking galaxies. Instead, they form a tangled lattice, threads of magnetism stretching across cosmic voids, binding distant galaxies into filaments and hubs. This isn't random. The structure looks deliberate, and it may have shaped how galaxies were born, how they collided, and even how matter itself spread across the cosmos. What's truly astonishing is how early this magnetic network appeared, just a few 100 million years after the Big Bang. It wasn't the product of slow cosmic evolution. It was there almost immediately, hinting that the infant universe had a surprising ability to self-organize. These magnetic threads may have guided matter, seeded galaxies, and even influenced their rotation. In a way, it acted like an invisible scaffolding, both supporting and controlling the physics of everything around it. Perhaps the most striking idea is how closely this magnetic web mirrors the brain's complexity. Each magnetic strand functions like a signal pathway. Each junction where threads intersect works like a hub of information. Together, the network could transmit physical effects across immense distances. And so arises a provocative question. Could the universe itself be self-organizing in a way that faintly resembles how a brain processes information? Not biologically, of course, but in terms of order, connection, and flow, the comparison feels surprisingly real. Simulations suggest that this ancient magnetic skeleton may have long-lasting effects, steering the birth of stars, galaxies, even black holes. Galaxies aligned along magnetic filaments tend to spin and form in coordinated ways, almost like dancers moving to the same rhythm. This could help explain why astronomers see synchronized galaxy rotations and bizarre cosmic collisions that were once mysteries. But magnetic fields aren't passive. They interact with matter, bend the flow of gas, steer the shock waves of supernovae, and may even affect the speed and trajectory of ancient comets like 3I Atlas. Far from being a static background, the magnetic web is dynamic, an invisible conductor shaping the universe like a silent hand at work. This discovery also reshapes how we think about planets and stars. If magnetic fields influence the way dust and gas clump inside stellar disks, then they may have decided how fast planets formed, which elements they carried, and why some worlds, like 55 Cancri e or SIMP 0136, are so bizarre. The early universe, then, may not have been a chaotic mess, but a finely tuned environment molded by hidden, powerful forces. Even the most violent places in space may be bound to this web. At the heart of the Milky Way, Sagittarius A Stai, our supermassive black hole, pulses with strange irregular flares, like an erratic heartbeat. Magnetic filaments might be channeling matter into it, dictating the rhythm of these cosmic beats. If so, magnetism isn't just a veil across space, it's an active player in the most extreme phenomena we know. Altogether, this hidden magnetic network suggests the universe is not a random void, but a vast, organized system. One with hubs, filaments, signals, and feedback loops, much like a living neural web. It is, in essence, an invisible backbone holding galaxies together, guiding matter, influencing star birth and planet formation, and perhaps even directing the behavior of supermassive black holes. And now, even the very heart of the Milky Way is whispering strange messages, those flickering pulses from Sagittarius A Stai beating like the restless heart of a cosmic giant, hinting at mysteries beyond the edge of physics as we know it. At the very heart of the Milky Way, hidden deep within a sea of stars and cosmic dust, lies an immense concentration of matter, millions of times heavier than our Sun, known as Sagittarius A. This is the beating core of our galaxy, a supermassive black hole whose gravity commands the orbits of billions of stars around it. Yet recent observations have uncovered a puzzling twist. Sagittarius A doesn't just sit in silence, swallowing matter. It pulses with strange flashes of light, irregular heartbeats, echoing from the edge of its event horizon. These pulses defy the models astronomers once relied on. Normally, supermassive black holes consume matter steadily, releasing energy in predictable ways through their surrounding accretion disks, or jets of radiation. But Sagittarius A flares in short, erratic bursts, its brightness spiking without warning. Like the arrhythmic beating of a restless heart, its rhythm can't be predicted, leaving scientists to wonder, what exactly is happening at the edge of this black hole? One leading idea is that these flashes are caused by matter plunging into the black hole at irregular speeds, sparking violent outbursts of energy in the accretion disk. As the material is dragged inward, crushed by gravity and heated to extreme temperatures, it blazes in X-ray and infrared light, brilliant but fleeting. Still, the sheer frequency and intensity of these pulses go far beyond expectations, hinting at physics we don't yet understand, or extreme cosmic events beyond the reach of current theories. Another possibility points to the black hole's magnetic fields. Twisted and coiled around Sagittarius A Stai, they may store up energy until they snap, unleashing sudden bursts of radiation. It's a process not unlike the solar flares we see from our Sun, but magnified millions of times in scale. What results is a kind of cosmic dance between matter and magnetism, where energy builds, snaps, and erupts into the flickers we now detect. Sagittarius A is also extraordinary for how it influences its cosmic neighborhood. Nearby stars, drifting clouds of gas, even ancient comets may be disturbed by its flares and radiation. Their orbits can shift, they can be torn apart, or they may spiral inward to be consumed in spectacular collisions of matter and light. Far from being a passive anchor of the galaxy, Sagittarius A is a restless engine of chaos, reshaping its surroundings in dramatic ways. These unruly pulses may also serve as direct probes of physics at the very edge of the event horizon, where gravity warps space and time to unimaginable extremes. Einstein's general relativity predicts bizarre effects there. time dilation, distortions of space-time, but Sagittarius A now gives us real evidence. Its flashes may be signals from an undiscovered realm of physics, offering rare clues about the true nature of black holes and gravity itself. Some scientists even speculate about a link between Sagittarius A star and dark matter. If these strange pulses somehow involve interactions with dark matter particles, it might explain mysteries in the Milky Way, from the odd movement of stars far from the center to the uneven distribution of gas clouds. A black hole entangled with dark matter could generate hidden streams of energy and matter we are only just beginning to glimpse. Looking closer at Sagittarius A star also opens bigger questions about how galaxies evolve. Its chaotic pulses could regulate star formation near the core, redistribute matter and energy, and create hostile environments for young stars and planets. It suggests the galactic center isn't a quiet anchor of order, but a turbulent hub that directly shapes the destiny of the Milky Way. What we're learning here also connects to the distant universe. Monster black holes devouring matter, young galaxies suddenly shutting down star formation, even vast cosmic magnetic webs, all may be better understood through the lens of what's happening inside Sagittarius A star. Its irregular heartbeat, then, is not just a local curiosity, but part of the broader story of how the universe builds and organizes itself. And if supermassive black holes already stretch the limits of what we think is possible, then dark matter, the invisible shell that makes up most of the cosmos, is even more unsettling. With its potential to warp galaxies, spark cosmic collisions, and weave immense bridges of stars, it stands as the next great mystery. A shadowy force waiting to reveal an entirely new chapter of cosmic violence. When we think about dark matter, most of us picture it as something passive, an invisible presence quietly surrounding galaxies without making any noticeable impact. But recent observations from the James Webb Space Telescope have begun painting a very different picture. One where dark matter doesn't just exist, but acts like a violent, powerful force, capable of tearing galaxies apart and forging colossal structures never seen before. Distant galaxies, when viewed through infrared light, reveal that dark matter isn't simply providing stable gravity. Instead, when galaxies collide or drift past one another, dark matter seems to interact, scatter, and fling material outward, creating vast streams stretching hundreds of thousands of light years. These streams can link galaxies together, form bridges of stars, or rip apart massive clouds of gas, leaving galaxies in chaos. It's direct evidence that dark matter isn't as passive as we once believed. It can drive some of the most energetic processes in the universe. One striking example comes from galaxy clusters, where enormous dark matter filaments stretch between galaxies, forming star bridges filled with gas, dust, and even newborn stars. These bridges act like cosmic highways, connecting galaxies across unimaginable distances. They show us that dark matter directly influences how normal, or baryonic, matter is distributed, shaping galaxies, guiding their evolution, and even affecting how fast stars are born. But dark matter's power doesn't stop there. When combined with the extreme effects of gravitational lensing, the universe becomes stranger than anything we could imagine. Gravitational lensing happens when the light from a distant object is bent by the gravity of something massive in the foreground, like a giant natural lens. In extreme cases, gravity can warp space-time so severely that a single galaxy appears multiple times, overlapping itself in bizarre, dreamlike reflections. These dramatic lensing events are not only breathtaking to look at, they're also priceless scientific tools. They allow astronomers to measure the mass of dark matter with precision, map how it spreads and interacts across galaxies, and test Einstein's general relativity on cosmic scales. Thanks to lensing, the invisible becomes visible. Dark matter structures, shredded gas streams, stretched newborn stars, all revealed in stunning clarity. The combination of dark matter's raw violence and the surreal distortions of gravitational lensing unveils a universe that is both chaotic and strangely ordered. The cosmos isn't silent or still. It's alive, shaped by hidden forces that rip galaxies apart, weave them together, and continuously remake the universe in a restless cycle. Every new observation is a reminder of the universe's elegance and unpredictability, far beyond anything we've expected. These discoveries also highlight just how crucial James Webb is. Every image, Every spectrum, every faint trace of infrared light isn't just data. It's a window into stories the universe has never told before. From hellish planets and ravenous black holes, to brain-like magnetic networks, to violent dark matter and surreal gravitational lenses, Webb reveals a universe that is endlessly strange, diverse, and beyond human imagination. And as Webb's work continues, the cosmic picture grows more paradoxical. Giant galaxies appearing too soon, black holes devouring matter at impossible rates, planets vanishing in storms of molten iron, magnetic fields as intricate as neurons, and dark matter behaving like an energy force instead of a passive backdrop. Each discovery reminds us that the universe isn't waiting for us to figure it out, and our imagination has barely grazed the surface of its mysteries. We are standing at the edge of a new era of exploration, where every day could bring a shock, where old theories collapse and new ones rise. And at the center of it all, James Webb watches like an endless pair of eyes, recording, unveiling, and inviting us into cosmic secrets we've never seen before. From the violence of dark matter to the warped beauty of space-time, this is our universe, wild, fierce, impossibly beautiful, and endlessly captivating.